As we start dynamics, we're just going to kick back into grade 11 physics and review some of the ideas that we had for dynamics from last year. So, of course, when we look at dynamics, dynamics is all about forces. So, you focus on the kinematics, which of course is the motion, and then you can start looking at the forces, which of course cause the motion to exist in the first place. Now, of course, when you guys started doing forces, you guys did a little bit in grade 10 science as well as in grade 11 physics. Of course, when you start looking at forces, of course, you typically start by looking at Newton's 3 laws of forces. And if we sort of paraphrased them last year, we adjust how we discussed them and stuff like that. But if you look at Newton's first law for forces, of course, this is where the term inertia comes from. So we would talk about inertia, where basically for different reasons, but we can sort of look at as objects actually resist acceleration. And of course, you'll hear, objects want to stay at rest, or if they're at rest, or they want to keep moving the same way. Basically, objects resist, quote unquote, acceleration. They don't want to accelerate. They just want to keep on going the way they're going or not go at all. So objects would kind of resist acceleration, and they sort of want, nice the way I looked, they want a constant velocity. And the velocity may be 0, but they don't want their velocity changed. They don't want to accelerate, and they will resist that acceleration. Okay, and of course, when you try to acceleration, you can feel it resisting against you. All right, that's basically Newton's first law. Now, of course, the second law, of course, is known as the calculation law. And it basically has 2 things. Talks about the factors of acceleration, and that acceleration is directly proportional to force, but not just any force. It's directly proportional to the net force, or the total force on something, and also acceleration is directly proportional to the inverse of the mass. So Newton's second law is more about the factors of acceleration, more than the actual force itself. And of course, we can put those 2 things together, and acceleration is then net force divided by mass. And of course, most people just remember it as F equals ma. Okay, no big deal. Okay, good old grade 11 review. And of course, the third part, or the third law, again, you'll often hear the action-reaction thing, but that's kind of not quite right, because reactions don't occur at the same time as an action. They're not simultaneously occurring, and the forces want to occur at the same time. So a better way to think of it is that forces always come, not come pairs, but come in pairs. There's always 2 forces. So forces come in pairs. There's always 2, and they are equal, and of course they are opposite. And sort of like we mentioned before, they have to occur at the exact same time, so they have to be simultaneously. And by saying action, reaction, you imply that they're not occurring at the same time, because a reaction always occurs after the action initially started. And that's just not the way forces work. So these are the basic things that we looked at in grade 11 for forces. We got the inertia, the F equals ma, and there's always 2 forces acting on an object. Okay, so these are just the baseline guidelines for all forces of all kinds, and they're pretty universal and handy to use. Okay, so let's also look at some of the forces that we actually looked at last year. And you guys looked at a variety of forces. We already talked about net force a little bit, which of course is a nice way to think about it is like total force. Some other forces you guys looked at was, we had applied force. So applied force can be a variety of things. I mean, there's lots of things that can apply forces, but we talked about FA quite a bit last year. We looked also at normal or natural force. And of course, this is what occurs between 2 masses when they're in contact with each other. You have to have 2 masses in contact with each other, and the normal forces are like the pressure force or the pushing force between the 2 objects. So we looked at that last year. Of course, that also directly connected into the friction. Okay, you guys looked at frictional force, and of course, this is often connected to the normal force, because you can't have friction unless you have 2 masses and they have to be in contact with each other. So there is a direct connection between those 2. So we've got the net force, we've got applied force, we've got normal force, or normal or natural force. There's those two names often get kicked around. We've also got the force of friction. Of course, you could also get into drag force a little bit with that, which is very similar to friction in lots of ways and how we can actually use it. We also looked, of course, at the force of gravity, okay, which of course is also known as weight commonly. So the force of gravity, another common one. So, I mean, these are the main forces that we did stuff with last year, you know, pushing on stuff and pulleys and a whole bunch of other stuff. These are some of the main forces that we looked at, and which ones come up depend totally on the scenario, the setup, the situation. It all depends on lots of different things. So we're just going to kick into some basic questions and practice using some of these things and associate them with some other, maybe some of the new kinematics that you guys have done. But let's just review some of the forces and some of the scenarios that you guys looked at last year. So let's take something pretty typical and easy. Here we go, you know, something like that. Okay, just a couple wheels. Okay, we've got a sweet car. Nice boxy car, so like from the 70s or something like that. All right, there we go. All right, so really, really simple. Okay, so let's say we've got a 1,800 kilogram car, and let's say it's going at let's go with 5.0 meters per second. Okay, and let's say it uses let's say use 40,000 newtons, okay, in order to accelerate. Okay, so let's say it uses 40,000 newtons for, well, actually, 40,000 is quite a bit. Let's go to let's just say 4,000 newtons. So let's say that car uses 4,000 newtons for, let's go with 7.5 seconds. So what would the new speed be? Okay, so just basic dynamics, kinematics type questions. So let's just start easy. All right, so we've got force, we've got mass, we can find the acceleration. So of course, acceleration is going to be net force divided by mass. Really, the net force is the only force we have. You could call this the, this is the applied force right there, that foreground, and it's the only force we have, so the net force would just be that applied force. All right, so we get the 4,000 newtons. We'll just divide that by the mass, which gives us an acceleration of about 2.22 meters per second squared for our car. Well, now that we have the acceleration, we can take that acceleration. We've got the acceleration, we got time. We can find the change in v for the car. So, of course, that would just be the acceleration, multiply that by the time, and that gives us a change in v of around 16.7 meters per second. All right, so we've got the change in v, 16.7. All we'll have to do is then add that to the 5 that we started with. So our final speed would just be the 5 that we started with, add that to the 16.7. And we have about 21.7 meters per second would be the new speed, just like that. All right. So let's see, what if we altered the situation a little bit? Okay, let's take the exact same car, exact same setup. Let's just modify it a little bit. Let's say the car only reached, 18 meters per second. So how much friction was there? Okay, well, let's find a couple things here. So first of all, we have the final speed was 18. The initial speed was 5. So it's going to change our change in speed. So our change in speed before was 16.7. Now our change in v is only going to be 13 meters per second, which means our acceleration will also be different. Okay, so our acceleration would be the change in v over change in t. So, the 13, that hasn't changed, so we got 13 meters per second, and we will divide that by the 7.5, and we can get an acceleration of about 1.73 meters per second squared. Okay, and once you've got acceleration, this is when we can find our net force, because of course MA always gives you your net force. So we'll use the 1.73, and then we'll times that by the mass of 1,800 kilograms, and we get a net force of 3120 newtons. All right, so if we sort of piece things together, our car is pushing with 4,000, but we're only getting 3120, so the rest must be lost to friction. So that means we're losing, give or take a little bit, we'll do it down here, we're losing approximately 880 newtons to the force of friction. Okay, so something simple like that. All right, okay, let's clean this up and let's try something else. Okay, so let's try, how about this? Let's try this. Let's see, we got some water here. There we go. We've got this little boat. Put the water. Prop, there we go. Motor, a little splashy splash. Okay, a little windshield going on. Alright, so we got a little person in their boat cruising along. And let's say they're cruising along here at, let's go 6.5 meters per second, and they're going to speed up. And over here, they are going, let's go with just 12.0 meters per second over here. Okay, and let's say they sped up over a distance of, let's go with 25 meters. Okay, now our water here is going to resist. It's going to resist the boat. Let's say with 400 newtons. Let's say the boat is, 800. Say it's an 800 kilogram boat. All right, let's change the color here. That's better. So 800 kilogram boat. All right. So what is the applied force from the motor? Okay, well, let's see what we got here. Resisting force 400, I got a couple of V's, I got distance. Actually, with these two V's here, I've got V1, I've got V2, and I've got a distance. I can easily use that to find acceleration with that new kinematic expression that we derived in the other part of the unit. So if we use V2 squared equals V1 squared plus 2AD, we can really quickly find out what the acceleration is. So let's see. So that'd be an acceleration about 2.0 meters per second squared. So there's the acceleration of the boat. Well, I've got the mass and I've got the acceleration, so it's really easy then to find the net force, of course, just ma. And with the 800 and the 2, that's going to be a net force of 1,600 kilograms. So that's my net force. So that's what the boat is actually getting. Well, if the water is resisting with 400 newtons, but I'm still getting 1,600, well, not kilograms, 1,600 newtons, if I'm still getting that much, that must mean that the applied force from my engine's got to be 2,000 newtons. So the engine's pushing with 2,000 newtons. The water resists with 400, so subtract 400, which leaves me with my net force of 1,600. So there we go. So now we can incorporate a little bit of the new kinematics in with this. You could have solved this question without the fancy year formula for kinematics, but it just makes it a little bit quicker, a little bit more efficient. All right, let's try another type of question that you guys did. Something else you guys did some basic pulley type stuff. We have like a couple of masses hanging on a pulley. So let's see, we get like a nice big fluffy cotton candy thing. Sometimes they got the little cone thing that they attach it to, something like that. And let's say on the other side, maybe we've got, I don't know, we've got, there we go, an ice cream cone, chocolate ice cream cone, something like that. There we go, something like that. All right. So let's say we've got a 2.4 kilogram ice cream cone, and let's say we've got a 1.1 kilograms of cotton candy. That's pretty dense cotton candy, and this thing is moving along, maybe rotating something like this. And let's say that the entire thing is accelerating at 1.5 meters per second squared, and I want to know how much friction is in the pulley. Okay, well, let's just piece things together. We've got a couple mg forces going on here. I'm going to do a little split here. There we go. We've got mg for the cotton candy. So if we do mg for the cotton candy, we can find out that the cotton candy is pulling on the system with approximately 10.8 newtons. And if we do the same type of thing for my ice cream cone, we can find that the ice cream cone is, use brown for ice cream, the mg for my ice cream cone is approximately 23.5 newtons. Okay, so there's my two pulling forces, and I often like to put my pulling forces together. So if I do that, I've got basically 11 going one way, and I've got about 23.5 going the other way. So if I just subtract those two, I can find out that those two forces put together would be about 12.7. So my total, I would probably call it my total applied force, is 12.7 newtons trying to go that way. Okay, all right, so that's my pulling forces, but I've also got the mass given to me. I've got that, and I've got the acceleration. So with those masses and acceleration, I can find the net force. So if I find the net force, it'll be F equals ma, and be the total mass put together, because they are tied together. So I'll take the total mass of 3.5, and I'll times that by the 1.5 for the acceleration, which gives me approximately 5.3 newtons. So I've got 12.7 trying to move it. I'm only getting 5.3, so I must be losing the rest to friction. So based on that, the force of friction must be the difference between the two. So the difference between the 12.7 and the 5.3, which would give me a difference of about 7.4 newtons. And of course, friction would be opposing the motion, so going the other way. All right, so there's a little force of gravity in there, similar to some things that we looked at a little bit last year. Okay, so let's clean this up again and try a couple other scenarios. All right, so let's try something else. You also did pulley questions like this a little bit last year. Something like this and something like that. There we go. All right, let's see if we can incorporate some other stuff here. Here, I'll use my fancy box tool here. I got the green box. All right, green box. And I'm also going to draw. Let's draw a red box. All right, something like that. And then we'll even fill them in, make them all pretty. There we go, something like that. Okay, so let's say we get two boxes. Let's say this box is 50 kilograms, and let's say this box here is 60 kilograms, and let's say the coefficient of friction between the box and the table is 0.20. So remember coefficient of friction from last year. So let's find a few things and piece things together. We're going to find out what is the acceleration of the system. Okay, well, let's just find out simple forces first. So easy for the box here. I can find the mg for the box. So that's just the 50 times 9.1. So that's really easy, because that's just going to be about 491 newtons. And of course, that force is trying to move the system. There's no other force actually trying to move anything. So that you could call that an applied force if you want to, no big deal. I can also find the mg for my green box. And if I do my mg, so it's 60 times 9.81, I can do the mg for my green box, which is about 589 newtons. And of course, that is actually causing pressure between the green box and the table. So that would be the normal force between the box and the table. Okay. Now, of course, really, really common is to then use normal force and the coefficient to find friction. So, of course, friction is mu Fn. So if I take that normal force and I times that by 0.2, I can find out my friction is about 118 newtons. Okay, so I think I've got all of my forces, all my basic forces ready to go. So let's see if we can piece things together. So how much is trying to move it? Well, the only force actually trying to move it is that 491 newtons. Nothing else. Okay, so what would slow it down? What's slowing it down? Well, that's of course friction. So that would be the 118 newtons. So I've got 491 trying to move it, 118 trying to slow it down. So if I subtract those two, that would give me my net force between the two. So the 491 and we'll subtract the 118, that will give me a net force of about 373 newtons. And then once I have that, I can find my acceleration, because of course that's net force divided by mass. So I'll take that 373 and divide it by the mass. Now, of course, I'll use the total mass because it's all tied together, it's all moving. So I'll divide that by the 110 kilograms. And I get an acceleration of about 3.4 meters per second squared. And of course, it's sort of going, the system's going towards the right. Okay, so there's some normal force, there's some friction, lots of good stuff. Okay, all right, let's check out another scenario here. Let's check out one more scenario. Hopefully this is a lot of this is looking familiar-ish to you. Delete that. Oops, still a little bit left behind. All right, delete. Okay, so let's try something else. Something else that you guys sort of looked at last year a little bit. Get a few things going on here. Here, let's draw surface, something like this. All right, and there we go. Draw a box. There we go. And have some, there we go. Let's take this. Let's put a rope on there. And then, there we go. Somebody pulling on the rope. Okay, so we got a box here. We can even shade in the box a little bit. There we go. Well, that's a little better. Okay, so we got a guy pulling the box. Hopefully this looks familiar. And let's say this guy is pulling with 700 newtons at 35 degrees. And hopefully with just this alone, you're going to recognize what we're going to probably do here is when forces are being pulled at angles, we've got to break apart the force into components to see what each of the components are doing. But we'll get to that in just a second. So he's pulling 700 newtons at 35 degrees. And let's say that the box is, let's just go with 20 kilograms. Okay, all right. Now he's moving along, and let's say he is in dynamic equilibrium. Let's see if you guys remember what dynamic equilibrium means. Okay, and we're going to find out what is the coefficient of friction between the box and the ground. So, of course, if you're in equilibrium, if you guys remember, equilibrium means no acceleration. All the forces cancel out, no acceleration. If it's dynamic, that means you are still moving. Okay, let's get to the basics. So first things we're going to do is we're going to break apart the forces into force X and force Y. So hopefully that seems familiar. Break apart the forces into Fx and Fy. So my force in the X direction is about 573 newtons. So he's pulling sideways with 573, and he is pulling up with, oh, actually it's supposed to be 57. Actually, oops, little mistake there. It's supposed to be 70.0 newtons, not just 70 newtons. Yeah, that's a little better. 70 newtons. There you go. Forgot the decimal. Okay, so pulling the side with 57.3 newtons sideways, and he is pulling up with about 40.1 newtons going up. So those are those two forces that he is pulling with. So between those two forces, how much force, and I often like to ask myself, how much is trying to move it? Well, that's that 57.3 newtons. The force in the x direction, that's how much is trying to move it. And then the 40 is actually pulling up. Okay, now I've also got the mass of the box. So really simple, I'm going to find the mg for the box because that's really simple. So if I find the mg for the box, that's just around 196 newtons, something like that. Okay, so let's see if we can piece a few things together here. It's trying to move with 57.3, but I know that since it's in equilibrium, I know that the net force has to be 0. So if the net force is 0 and 57 is trying to move it, that tells me that my force of friction must be negative 57 newtons. So 57 is trying to move it. Friction must be 57 to cancel it out, which gives me net force of 0, and this thing can be at equilibrium. Okay, well that's going to come in handy, because if I go back to basic coefficient of friction is FF over Fn, and I figured out what my friction must be. Now I just got to figure out what my normal force would be. Now, if the box was just sitting there, the normal force would be 196. But since he's pulling up with like 40 newtons, it's going to be a little bit less. So the normal force will start as the mg, that's fine, that's the 196, but I got to subtract what he's pulling up in the y direction with. So if it's basically 196 for mg, he's pulling up with 40, my normal force is going to be left with about 156 newtons. So that's got to be my Fn. So I know this is like 57.3. This right here is going to be 156. So then all I have to do is divide those two out. And of course, coefficient of friction has no units because it's a ratio between forces. And I get a coefficient of about 0.37. Okay, so there's some coefficient of friction, force of friction, normal force, Fx, Fy, mg, applied force, net force, basically one question of the whole bunch of different types of forces that you guys were introduced to last year.